So, main aims today, then using formulae, review of engineering notation in standard form, how we represent large and small numbers. I want to introduce you to this idea of presenting data and the assignment 3. So I'll point you at some questions to have a go at, and you can then maybe do that and then get on with assignment 3. And then at the end, if we have time, as I say, we'll look at rearranging formulae. Okay, so calculators you will need. We had a formula last week, one of the formula that we wrote down, which was to find the total resistance, RT, of two resistors in parallel. So RT equals R1 times R2, plus R2 over R1 times R2, and in fact, that's the wrong way around. Well, good job, I noted that. Product over sum is the way I remember it, so that's why I recognise that was the wrong way around. So we need to know the values of the two resistors. So here we go, R1 and R2. And then we can work out the resistance. Now, what I want us to do is and that's why I want you all to have access to these scientific calculators. They have on them the capacity to do the calculation in one hit. And that's what I want you to do. So if you look at your calculator, you'll see that it's got on it a fraction button. If you've got a scientific calculator in front of you, generally on the left-hand side, if you've got one of these Casio calculators and I were to hit that button, I would see this on the screen. Roughly, I'd see a flashing cursor at the top and then a line and then something below. So you can actually put in a fraction. And so what I can do is, if I've got that facility on my calculator, is to key in literally this formula, R1, so that's 136.58, times R2, which is 53.6, and then move my cursor down to the bottom of the fraction button using the arrow key, and then put in 136.58 plus 53.6. And then I can look at it and compare it with what it should look like. And so I know I've not made any mistakes. And then I can hit the equals button. And I get a solution with all the accuracy held in the calculator. And then I decide how much accuracy I can afford to have. And so I look at the numbers I put in. And this one is to 5 significant figures, 5 measured values. This one is to 3 significant figures. So the rule of thumb is I look for the least accurate value, which is this one, 3 significant figures. And then I give my answer to that or one more. So I may be tempted to go to one more because this is to 5, but certainly no more than 4 significant figures. So write down the answer. Can you do it to both? So we can compare them. 3 significant figures and 4 significant figures. So Lee, what would it be to 3 significant figures? Now, what you've done there, Lee? What have you? Right. No, not quite. Yes. You've given me 3 decimal places, okay? We don't use decimal places, and I'm glad you did that anyway, because it's a reminder from last week. If we think of units like meters and millimeters, that's meters and that's millimeters, that's the same length. They're both 4 significant figures. One is 3 decimal places and one is no decimal places. So as far as accuracy is concerned, decimal places are meaningless because the position of the decimal point just depends on the unit. What we're interested in is the significant figures, which is the same in both. So we never quote, although some people I'm sure will, and lecturers do tend to use it, but I think inaccurately. Stick to significant figures. So you're right, Lee, it's 38.5 to 3 significant figures. And to 4 significant figures, 38.49. So maybe this is a case that because that's so close to 5, I'd probably quote it to 3 significant figures. And what have we forgotten to put on it? The unit, ohms. So to give an accurate answer, quote the value to an appropriate accuracy and put in the unit. Okay. If you don't have this fraction button on your calculator, then you can do it in one hit, but what you have to be aware of, and this is the key area of error actually, is if I divide by 136.58 plus 53.6, I've got to make sure that's in a bracket, because then it will divide the top by all of the bottom, which is what you want. If you don't put the bracket in, it will just divide by 136.58 and then add 53.6 at the end. Okay? So if you don't use the fraction button, remember to use brackets, so the calculator knows you're dividing by that whole term. Okay. Here's another one that I want us to look at. Okay. This is a formula 2 to find the total resistance for resistors in parallel. So in fact, we were talking about this last week, I think. You can show that that formula we looked at on the previous slide is the same as this one. So now I've got 2 further resistors, R1 and R2. Now what I want to do is to show you how to get the calculator to do this in one hit and hold all the values in it. I want us to avoid writing down answers as you go along. So, a few things to note about this. 1 over R1 or 1 over R2 or 1 over RT means the inverse of R1. So when I say find 1 over R1, I could easily have said find the inverse of R1. Inverse means 1 over. Okay? And inverse means inverse has the same meaning as invert in common language. So when you invert something, you turn it upside down, and that's what we're doing here. Take a number, 1 over 3, inverse of this is 3 over 1. Flip it. 1 over something, find the inverse of it, turn it upside down. The inverse of 3 now for this one, we never write, look at this number 3, we never write this as a fraction, but it is a fraction. It means 3 whole ones. So what I could do is write 3 whole ones, 3 over 1, but we never write it. So any number, any integer, could be written as over 1, but obviously we wouldn't bother to do that. But if we're thinking of finding the inverse, we need to remember that actually that's what it means, because then when I invert it, I get 1 over 3. In other words, the opposite of the one we just looked at. Okay? So to invert a number means to write it upside down. And you've got a button on your calculator that will do this. Can be written as to the power minus 1. For reasons that we will look at when we do the laws of indices. So another way of writing the inverse is to the power minus 1. So the inverse of 3 is or equals 1 over 3 or 3 to the minus 1, 3 to the power minus 1. So this is the sort of notation we use to mean the inverse. I'll just pause while you dive. Look at your calculator. You've got a button on your calculator that will give you this. So the inverse of x, remember we're going to be talking about this unknown value x. So x is a number, could be 3, but we just don't know what it is. So the inverse of x is 1 over x, or x to the minus 1. And if you look at your calculator, you've got a button on there that either says 1 over x or x to the minus 1, and it means inverse. So I'm going to use that button to use this formula. If I want to know what 1 over R1 is, I just key in 36.5 and then hit the inverse button. It gives me 1 over it. So the quickest way to use this calculation is to do this. So we've got that 1 over RT equals 1 over R1 plus 1 over R2. So 1 over RT equals 1 over, what's R1? 36.5 plus 1 over 14.62. So this is what I would do on my calculator. I would key in 36.5 and then I would hit the 1 over x button, and I get on the screen 36.5 to the minus 1 probably. So it's telling me it's the inverse of it. And then I'm going to key in plus 14.62, and then I'm going to hit the x to the minus 1 button again, or the 1 over x button again. And then on the screen I'll see plus 14.62 to the minus 1, the inverse of 14.62. And then I hit equals. But I'm not interested in that number that when I get when I hit equals. Why not? What does that answer tell me? Yes, it tells me 1 over RT. So I want the inverse of that. So I have a button on the calculator, I have a number on the calculator, and I hit x to the minus 1 again. And it tells me x to minus 1 of the answer, does it? I'm trying to remember without doing it as I'm going along, because my calculator's all out. And then, so x to the minus 1 answer, that's what you'll see on the screen, I think. And then if you hit equals again, you then get the solution. And what is that solution? Exactly. So what have you done? What have you got to put at the end? I don't disagree with your answer. Ohms, but what goes at the end? 3 significant figures. Have you rounded that to 3 significant figures? Is it exactly 10.4?
No, that's
Right. Right. So to 3 significant figures 10.4 or 10.43 to 4 significant figures. Either of which is appropriate, because if you look at these, I've got 1 is 3 and 1 is 4. We all get that? Does your phone do that? No. Okay, so that's another reason why it would be a good idea to have one of these, okay? Because they do actually allow you to put in pretty well what you see on the page, if you know which buttons to press. Okay. Right. Look at this one. Okay. In theory, they give the same answer. Here's two values. In fact, I'm going to change the values because they're the same as I think the ones we've just been doing. I want you to use both formulae in one hit on the calculator, come up with the answer, and you should get exactly the same answer both ways. So to force 5 significant figures, 30.198 ohms agreement, just write down, because it's a useful exercise, what that would be to 4 significant figures, because that's not immediately obvious. What would it be to 4 significant figures? And that's not straightforward, so give it some thought. So somebody on the middle bench, what did you get to 4 significant figures? Well done. 30.20 ohms, yes. Good. I'll round that. I'm going to round this up. This 9 needs to be rounded up because the next digit is an 8. But it's 9, so that means I must round the next one up to a 2. So I could write 30.2, but that would only be 3 significant figures. Actually, that now 19 effectively here becomes 20. So I need to write the 0. Well done. So this is a case of where I'm actually making a 0 significant. If I hadn't written 30.20 to 4 significant figures, somebody might quite rightly conclude that that is only accurate to 3 significant figures, because normally zeros at the beginning of the end of the number are not significant. And so in cases where it is significant, like here for example, you need to make sure, you need to state that it's significant. So, good. Okay? Okay. Circle. I'm going to expect you to know the formula for a circle after today, which if you didn't know it already. The formula for the area of a circle is pi r squared, where r is the radius. So just a bit of information about circles. The distance all the way around the outside of a circle is called the circumference. The distance right the way across is called the diameter. And the distance from the middle to the outside is called the radius. So if you didn't know that, make a note and memorize it, okay? Find the area of this circle, given that the diameter is 3.6 centimeters. So I'm just going to pause for a second while you do that. And of course, again, give your answer to an appropriate accuracy. Okay, let's have a look at it. So, what would I key into the calculator? Pi. And if you look at your calculator, shift and then one of the buttons at the bottom will give you pi. So we don't put in 3.142, any rounded estimation of pi. We use the pi button, multiplied by the radius. So the diameter is 3.6, so the radius is half that, which is 1.8. And then I hit the x squared button. So you've got an x squared button in the calculator, which gives you squared. And again, with these calculators, that's what you see on the screen, pi times 1.8 squared. So you can check you've put in the numbers correctly. And then you hit equals and you get the answer to loads of decimal places, and then you give it to an appropriate accuracy. So what would you put? 10.2 to to 3 significant figures. Unit. Yeah, centimetres squared. Square units. Why centimetres? Because that's what I measure the diameter in. So square centimetres. Okay. Ah, yeah, good point. I was going to make that. If the answer comes up as a fraction, then this button was the one to use. SD. S stands for surd. Surd is a name for a fraction, a number written as a fraction. So fractions to D for decimal. So you can convert it to decimal, doing it that way. Sometimes you want the answer as a fraction, though, so that's often quite a convenient way to get the answer. But if you particularly want a decimal, then that's the button. Okay. Here's a cylinder, something that we're not too long before we're going to be thinking about fine volumes and areas of common shapes, and so the cylinder is going to come in. The formula for the volume of a cylinder is the area of the end. So for a cylinder, what's the area of the end? Pi r squared times by the length. So here's the formula, pi r squared L. So that's the length, and it's got a radius r. So I measure the length of this thing as and I measure the radius as that. And those two numbers are written in what's called engineering notation. This is engineering notation. So we need to talk about how that's arrived at and how it works, for those of you who are not sure. Okay? The calculator allows us to put numbers in engineering notation, or standard form actually, and we'll talk about what that is. And it's a way of expressing very big numbers, so this is quite a large number, and small numbers, this is a small number. There's a section in the textbook which takes you through how these things work, but just a quick look at them and how it works. So if I have a large number, we'll come back to this problem and work our way through that. So for large numbers, one, 3, 6, 0, 0, 0, 0, 0, 0, 0, 0, for example, then it's not convenient to write that number. Okay, and we can get bigger numbers than that, and so we need a shorthand way of writing these numbers. What we do is we remember that to multiply by 10, we just move the decimal point one place to the right. So what I do is I move the decimal point to a convenient place, like after the 6, 136, and I ask myself how many times I've moved it. And then I multiply it by 10, that number of times, to get it back again. So if I've moved the decimal point from where it should be, which is here, so there, 136, then I've got to times it by 10. 1, 2, 3, 4, 5, 6, 7, 8, 9 times to get it back to where it should be. So I'm going to multiply it by 10 9 times. And the shorthand way of writing that is 10 to the 9. 10 to the power 9 is 10 times 10 times 10, 9 times. And that's engineering notation in a nutshell. The key with engineering notation is it must go in threes. the power must be a multiple of 3. So I could have written 0.136 times 10 to the, what would go there? So if I move it not from there to there, but I move it from there to there, how many times have I got to move it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So because I've moved it 3 places further back, I've got to now add 3 to this number to make it 12. So that too is in engineering notation because it's a multiple of 3. Standard form has a different convention. Standard form always, and that's a key word, always moves the decimal point to the right hand side, I'll use a shorthand there, of the first significant figure. Always. Scientists, mathematicians tend to use standard form. So they move the decimal point to after the first significant figure. Engineers tend to use engineering notation. And the reason why they do that is because these multiples of 3 fit themselves perfectly to prefixes like kilo and mega and milli and micro and stuff like that, because they would go in 3s as well. So we will stick to engineering notation. But you'll come across standard form. So for this number, in standard form, it would be 1.36. So in standard form, we would write 1.36 times 10 to the, how many times do I have to move it now to get it back to where it should be? 11, right. Okay, which is not a multiple of 3. All the answers are correct, but that's standard form, the other 2 engineering notation. So that's a very quick note on engineering notation and standard form for large numbers. Small numbers, it's exactly the same idea. Naught point naught 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 136. Now what I do is exactly the same idea. I want to move it to a convenient place, say here, from there. So it was there, it's there. So, but if I move it to there, I've now got to not multiply 10 by 10, I've got to divide by 10. Okay? I've got to divide by 10 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times to get it back to where it should be. Divide by 10 is the same as finding a tenth, the inverse multiplied by the inverse. Remember, inverse is minus, as we'll see when we look at the laws of indices again. So this equals 136 times 10 to the minus 12 in engineering notation. Or, again, in standard form, I'd move it to 1.36 times 10 to the minus, there's where I'm going to go to. So I've got to go back 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 to the minus 10 in standard form. There is no right answer for this, for the engineering notation. It all depends on where you want the decimal point to be and what units you're using. So whereas 136 times 10 to the minus 12 is good, so is 0.136 times 10 to the minus 9. And you might well want to use that. So there's no one answer. So long as it's a multiple of 3, it's in engineering notation. Comments? Okay, the only thing now to consider then is, how do I put these numbers to do this into the calculator? So if you look at the calculator, at the bottom of the calculator, this bit, to enter this into the calculator, I've got a button that allows me to do times 10 to the x button is right at the bottom. Or if you've got an older calculator, it might say exp, which stands for the exponent, which is the power. So how would I key this number into the calculator? I would key in 12.4, which is the numbers, and then I would hit the times 10 to the x button, which gives me my times 10 to the, and then I've got to put in the power minus 3. So the minus sign, if you look at the calculator, you've got a button with a minus sign in a bracket in it, or some of them have a plus minus button somewhere up on the left hand side. That's how you change the sign of the exponent to negative, and then you would key in the number 3, and that would give you 1.24 times 10 to the minus 3. Not 1.12.4 times 10. You don't key in times 10. If you do that, you're actually multiplying it by 10, and you'll get a factor. You'll be a factor of 10 out, and that'll be a mistake somebody will make. This button is the one that allows you to put the exponent in, the standard formula or the engineering notation. So how would I do this? The volume equals pi, so I hit the pi button, times the radius. What did I say? This was the length, didn't I? So that's the length, and this is the radius. So radius, which is 12.4 times 10 to the minus 3, and then I hit the squared button. You don't need to put the bracket in because it will know this is all one number in standard in engineering notation, but if you're worried about it, you can put a bracket in there like that so you can see it, times by the length, which is 3.6 times 10 to the 3, and then you hit the equals button and give me an answer to an appropriate number of significant figures, which is, sorry, 1.74. Oops. Exactly. No. Okay, so the 3 significant figures, but no power of. No. Unit? Millimeters cubed. Agreement? Yeah? Yeah. Comments? Okay. One more. Here's a sphere. Radius 3.6 times 10 to the minus. I want that in engineering notation, so what should I do to change this to engineering notation?
Multiple of 3.
Pardon? Multiple of 3. So how do I move the point to make it a multiple of 3? I can do it either way. That minus 4 means I'm going to go back 4 places. So if I go back 1, how many more have I got to go? No, minus 3. Think about this minus sign. It means minus means I'm going backwards with the decimal point. So if I go back 1, I've only got 3 to go. If I wanted to say this same number times 10 to the minus 6, what would this number be? 360. Right, I'd have to move it 2 places to the right to make it in engineering notation, or 1 place to the left. All of those are the same number. So if that's the radius, I want you to find the volume, and the formula for the volume is 4/3 pi times the radius cubed. So which buttons would you press on the calculator to do that in one hit? Let's have a look at it. 2 ways we can do this using the fraction button on the calculator. So this is an important button, this fraction button. Volume equals, I can use the fraction button and key in, using the fraction button, 4/3, 4/3. And then I can scroll along to the right and then put times pi and then times the radius, which is 3.6 times 10 to the minus 4. And again, you don't need to put the bracket into the calculator, but to write it on the page, always put the bracket in to avoid confusion, to the power 3. So that's one way I could key this into the calculator. Use the fraction button to put the 4/3 in, times pi times 3.6 times 10 to the minus 4 cubed, or any of these 3 would do as the numbers to be put in. The other way to do it, using the fraction button, and remember that from the drill, 1/3 of something is the same as divided by 3. So instead of finding 4/3 of it, I could do 4 times pi times 3.6 times 10 to the minus 4 cubed all over 3. So I can use the fraction button and say the volume equals, again, use the fraction button, and on the top of that goes 4 times pi times 3.6 times 10 to the minus 4 cubed, and then underneath goes the 3. They are the same thing. And you get the same answer both ways. So it's whichever way you think is easiest to put into the calculator. But don't forget that little thing, that they're the same. It will keep coming up, that little thing, especially in algebra. Okay. Now if we look at the textbook, I want to show you where some questions are. So I've got a sort of a electronic version of this thing here. If you look at there's a chapter on indices, standard form and engineering notation, chapter 2. So if you want a bit more practice on those, just to get yourself happy with them, if you've not come across them before, look at that chapter. If we carry on down, we've got some work problems on standard form and further work problems on standard form using these very big and very small numbers. There's a section on engineering notation, common prefixes, so the micro, milli, mega, kilo, all that sort of thing, if you're not familiar with that. And then when you've done that, chapter 4, calculation and evaluation of formulae. So using formulae, evaluation of formulae, chapter 4, section 4.4 is a good section to look at. So make a note of that. Chapter 2 and chapter 4 to have a look at in your textbook. Particularly the last sort of questions in chapter 4, using formulae. Good calculator practice, if nothing else, getting used to your calculator. So if you've not got one of these, the sooner you buy it, the sooner you'll get used to it. Okay?